Okay, so when we're talking about orbital notation is just a way that we can show how electrons are arranged around the nucleus of an atom. So this first blank here is going to be electrons. And orbital notation is just the process of writing out all the different orbitals and all the electrons that are going to be around that atom. And there are 3 different rules that we have to follow whenever we go through this process. You don't really have to know the names for them. You just have to be able to apply what it is they're telling us. So the first one here is Aufbau Principle, and it just tells us that electrons are going to enter those energy levels that have the least amount of energy first. So orbitals of lower energy get filled first, and then those that have higher energy are going to be filled later on. And you might think then that the order in which those electrons would fill in the energy levels would be all the 1s, all the 2s, all the 3s, all the 4s, all the 5s, etc. But that's not how it actually works out. So we're going to put a big ol' X through this, because there's some overlapping that occurs. There are some of the energy levels that have higher energy that actually are overlapping and will come before those that have a little bit lower energy levels. So it's because of overlapping that we're going to see a different order. And the order is still going to be easy for us to figure out because all we have to do is look at our periodic table. The periodic table can be used to determine the actual order of the sublevels. So let's go ahead and look at our periodic table that we filled in. You're seeing that we're starting with 1s in this first row. The helium is part of that. We're putting it over here with the hydrogen. So we have 1s. And then when you look at the second row, we have 2s and 2p, 3s, 3p. Everything's been in order. We would think that 3d would be next. But if you'll notice, after 3p, we move on to the fourth row. And what does it start with? 4s. And then it skips back down and we get 3D. So this 4s is the first energy level that's kind of overlapped where we're going to encounter it before we actually see 3D. And then once 3D is full, then we can go ahead and fill 4p, and it just continues row by row. We just follow the order that's on this periodic table. And we're going to be practicing with it as we go through today's examples. Okay, our second rule is the Pauli exclusion principle. It's named after a scientist whose last name was Pauli, and he basically said what we talked about on Friday. No 2 electrons can fit in the same orbital, the same space, the same amount of time, okay, or at the same time. So we're going to have how many electrons in an orbital? 2 of them can fit there if what is true about their spins. They have to have opposite spins. So you can have 2 electrons in an orbital, but so they're not occupying the same space, they have to have opposite spins. Remember we said one could be clockwise, the other one counterclockwise, or you might say one has an upspin, one has a downspin. But that way they're not in the exact same space at the exact same time. So in every single orbital we draw, which we're going to draw as little dashes, we have to be sure that there's 2 electrons in every orbital before we move on to the next one, but we can't have more than 2 within an orbital. Okay? And then this last rule probably really won't make sense until we actually see it written out. But Hund's rule tells us that whenever those electrons are entering the orbitals in that very last sublevel, that there's going to be 1 electron entering each orbital with all the same spin, all parallel spins, all facing up, until every orbital has 1 electron. And then if we need more than that, then we'll go back and put a second electron in the orbitals. So we'll do an example where you'll see. But you're going to have 1 electron entering each orbital until they all have 1. And then we'll go back and fill in that second one if we need it. Sometimes we don't need it. So let's actually show you how this is working. We're going to look up nitrogen on our periodic table, and we're going to look up 2 things. Okay. We're going to look up the atomic number. What's the atomic number for nitrogen? The atomic number is 7. What does that tell us? Okay, if it's neutral, there's 7 protons, and if it's neutral, there's also 7 electrons, which is what we're dealing with right now is electrons. So there's going to be 7 electrons that we have to draw on the paper. And then what sublevel is this element in? 2p. So we're going to write both of those things underneath the name nitrogen. We're going to put that we're going to have a total of 7 electrons, and that we're going to stop when we get to 2p. And what we're going to do is we're just going to start at the very beginning, and we're going to list every sublevel until we get to 2p, which is not going to be very much for this one. So let's just go row by row. If we start at that first row, what sublevels do we have in row 1? 1s. Okay, if you don't really remember how many little orbitals we're going to draw, how many do we have for S? 1. For P, we're going to have 3. For D, we're going to have how many? 5. And then for F, we're going to have 7. Okay. If you want to put a little reminder up here at the top of your periodic table, you can put S1, P3, D5, F7. That's how many orbitals you're going to draw, which are your little dashes. Okay. It's the same every time. It does not matter what row it's in. If it's an S, it's 1 blank. If it's a P, it's 3, etc. No, but I will. Just remind me after we do this. Okay, so if we're listing all of them through nitrogen, the first one we have is 1s. So we'll draw a little dash and we'll put 1s underneath it. And then we're going to leave a little bit of space, and then we're going to put the next one. What's the beginning of the second row? 2s. What's after 2s? 2p. How many little dashes for p? 3. So I'm going to leave less space between each of the orbitals within 2p. You'll kind of see how I've grouped those together so you know that they're in that one sublevel together. Now, everything before that very last sublevel has to be full of electrons. You're not going to have a sublevel earlier that's empty if you're putting electrons further on, because it has to fill the lower energy level first. So we're going to have an upspin and a downspin electron in both of our S sublevels. And once you've filled everything before that very last sublevel, then you look and see, well, how many more do I need? How many electrons have I put on the page? Each arrow is an electron. I've put 4. How many more do I need? 3 more. So Hund's rule tells us we're going to put 1 in each orbital until we run out of space, and then we go back to the beginning if we need to put a second one. So we're going to have 1, 2, 3. If I needed a 4th one, then I'd go back and put a down arrow in that first little orbital. Okay. Now, a quicker way of finding that out, this one was very quick, but if I look at the 2p section, how far over is nitrogen? It's the third one over. So the position of the element within the sublevel actually tells you how many electrons need to be written down within that sublevel, because each element is represented by 1 more electron being drawn on the page. Okay, so let's try another one. Let's try iron. What is the atomic number for iron? The atomic number is number 26. So there's 26 electrons. In what sublevel do we find that in? 3D. So we're going to list all of our sublevels until we get to 3D. So first row we have 1s. Second row we have 2s and 2p. Okay. Third row, 3s and then 3p. Okay. Fourth row is when it gets funny. We start with what? 4s. The very first sublevel in every row is always S, and it's always the number of the row. So the fourth row starts with 4s. But then when we get to those transition metals in the middle, that D block, the number is actually 1 less than the row number. So instead of 4D, it's going to be 3D. And how many orbitals do I draw for D sublevel? 5. Now, sometimes in textbooks, you might see like a box drawn instead of the little dashes, and then the arrows are just drawn inside the box. A quicker way of drawing these arrows, instead of having full arrows, you can do like a half arrow. And the way you're going to do that is you're going to start and you go up and then down. And then you go back up to the top and you go down and then up. And it looks kind of funny, but it allows you to go a lot quicker. You can just go and fill them in like this and not have to spend all day with your arrows. So that's a way you can do it a little bit quicker if you would like. So up, down, down, up. Now you'll notice I did not put any in 3D yet because I don't know how many I need to put there. I could put 1 or I could put 10. I can put anywhere within those two numbers. So I have to figure out how many I actually do need to place there. So let's go and look and see where iron is in that 3D sublevel. How far over is iron? It is 6 over. So that means that we need 6 more electrons. If we counted how many were already on the page, we should have 20. And if you want to kind of double check your work, you can do both of those. Count them and go and look and see where it is on the table. So if I need 6 more, am I going to go 1, 2, 3, 4, 5, 6? I'm going to go up in all of these and then down on the first. There we go. Hund's rule tells us that this is not what it's going to look like. They're going to spread out as much as they can to start with, and then when they all have 1, then we'll go back and put that second one. And we haven't started filling in our quantum numbers yet, but we will look at that more tomorrow, and we'll be looking at this very last electron that we wrote down in order to find those numbers. But we'll wait and do that tomorrow. Okay. Any questions on this one? Okay, one more. 10. What is the symbol for 10? SN, and it is number what? 50. So we'll have 50 electrons. It used to be called stannum. So, and what? 5p. Now this one we're not going to be able to fit it all in one row. We'll have to fit on 2 rows, and that's okay. So in the first row we have 1s. Second row, and 2p. Third row, and 3p. Okay. Fourth row is when it gets funny. We start with 4s, but then it goes to 3d. Then back up to 4p. So we go down a number and then back up. Then we move on to the fifth row. We start with 5s. What's after 5s? Close. Jamie. So after 5s, we do have 4d. And you're supposed to take your iPad if you have it. Okay. And then after 4d, we go back up to 5p. And that's where 10 is, so that's where we're going to stop. One thing I want to point out to you real quick before we go and fill in these electrons, if we did need to go further, if we had gone past 5p and then we went and we got 6s, what's going to come after 6s? 4f. Remember, these 2 rows down here actually fit into that little gap. So on your periodic table, if that really doesn't stand out to you, you might want to kind of like go over the lines, or you can even write down here at the bottom that whenever you get to those bottom 2 rows, this is the order you go through. For the 6th row, you'd go 6s, we'd come down here, we'd get all of 4f, and then we go back and get 5d, and then 6p. So if you want to jot that down on your periodic table, you can. Okay. Because there's one problem in on your worksheet where you'll have to go down and go through this F sublevel. Okay, so let's go ahead and look and see where 10 is before we even start drawing our arrows. How far over within the 5p sublevel is 10? How far? 2. It's 2 places over. So actually, again, like I told you, each one of those elements is going to be a new electron on our paper. If we have this as our 5p sublevel, if I just have one up arrow, that's going to be indium here. If I have a second up arrow, that's going to be 10. If I have a third up arrow, that's our antimony there. And then when you get to tellurium, that's a down arrow right there. Another down arrow, iodine, another down arrow, xenon. So each electron is a different element there. So we just need 2 electrons to get our 10 right there. So everything gets full. Everything is full of electrons except for 5p, which is only going to have those 2. So everything else. And we will find a shorter way to do this in the future, but we've got to kind of go through the long way to be able to understand what the short way is. So we'll fill in all of those electrons. And every one of these orbitals has to be full until you get to this last sublevel. The last sublevel can have some empty orbitals, just so long as there's at least one electron in it. If there were no electrons, you just wouldn't write it. It wouldn't be there. Okay. Do y'all have any questions? Okay. On your assignment, there's a column over on the right-hand side for putting the quantum numbers. Again, we haven't quite gone over that yet, so go ahead and just leave that part blank for right now. We'll look at that tomorrow. But we are going to go ahead and draw the orbital notations for those 4 elements. And I'll go ahead and do lithium with you real quick. We're going to put that it has 3 electrons. It's in the 2s sublevel. So you've got 1s, 2s, 3 electrons. That was the easy one. So you have 3 more of them to look at. We have about 10 minutes left. So you can at least get calcium and probably selenium done before you leave today. But don't turn it in because we are still going to look at the quantum numbers tomorrow.